In this video, we're going to be looking at 7.1, which is an introduction to functions. So the objectives of this section are to understand correspondences and functions, to understand functions and their graphs and what we can learn about a function from its graph, and to understand function notation and function equations. Basically how we write a function. We have 5 vocabulary words here. I'd like you to make sure you get them into either your vocabulary section of your notebook or your vocabulary note cards. Notice that each of these 5 words has a common definition in English that is going to be different from the mathematical definition in terms of functions that I'm giving you now. So especially when that happens, we need to be especially careful to keep track of what the mathematical definition is. Because in this course, we're speaking math instead of just plain English. Okay, so we need to really keep those separate. I'm a big fan of the vocabulary section of your vocabulary note cards. So a correspondence is just a relationship between two sets of numbers. Just think about ordered pairs. Basically, that's the kind of thing we're talking about in a correspondence, where one set of numbers is your x-coordinates and one set of numbers is your y-coordinates, say when you're graphing a line. And the domain is the first set in a correspondence, so the domain is the x-coordinates. And the range is the second set in the correspondence, or the y-coordinates. Function, the big idea going on here, the big definition in this section, is that is a correspondence where each member of the domain corresponds to one and only one member of the range. It's kind of a monogamous relationship between sets. They all get paired up, but the x's can only be associated with one y. Now, it's not fully monogamous because two different x's could be associated with the same y, but each x has one and only one y associated with it. And a relationship says an x can have more than one, they just have to have at least one in the range. So here's this little graph of a function. And let's talk about what we can figure out from the graph. Well, we can figure out what, say, for instance, let me grab the pen. What is x when y is 2? Well, right here is where y equals 2. It's the only point, if we drew a little hashed line through there, be the only point that would cross our curve at all. What is x there? X is 3. How about when x is negative 2? What is y when x equals negative 2? Well, right here, x equals negative 2 and y is 1. So here's a visual way that we can look at a function that has been drawn for us and see what some of those correspondences are between x's and y's. There's an algebraic way to do things too, and so we want to start to move towards function notation and what a function equation looks like. So here is a function machine. I'm going to move it up to the corner here. A function machine. You might have seen one of these at some point. I remember seeing them when I was in school, sometime pre-college, can't remember when, but I liked function machine. I thought they were kind of cool. I kind of would imagine them making these chugga-chugga noises as they figured it all out, and it was kind of entertaining to me as I was learning the math. So there you go. But basically what a function machine is it takes in an input, an x value, and it has some kind of rule in there that when an x comes in, this needs to happen to it, and then this needs to happen to it, and then this needs to happen to it. And then it'll get put out as output, and we'll call it f of x, because we've applied the function rule to it, whatever that is. Okay? So, when we look at a function, you'd be used to looking at something like y equals 3x plus 2. Whoops, plus 2. But here, we're going to say f of x. We're going to call the output the function of x, f of x. These parentheses, you know how they usually mean multiplication? Here they don't. No multiplication involved. We read this f of x equals 3x plus 2. And we're being asked to figure out what f of x would be. If f of x is 3x plus 2, what would f of x be for x equals 5? So let's think back to earlier on in algebra, when you'd be asked to evaluate this expression, 3x plus 2 for x equals 5. Basically the same steps here, except we're using our function notation and our function equation form. Okay? So now we'll say f of 5, instead of this just generic little x out there, we have a specific x that we want this information on. F of 5 equals 3 times 5. And I always put the 5 in parentheses, especially if you're going to multiply it by a negative number, or it's a negative number, or you can square it or something. It can get, negatives can get lost easily if you don't do that. So that's my caution to you. Plus 2. So we find that f of 5 equals 15 plus 2, or when we get right down to it, f of 5 equals 17. Little note about formatting and about how you should be doing all of your written work, even if it's written work in your notebook that you know you're not going to turn into me. Everything should be worked vertically down the page. Each step you take should be another line on the paper, always. And answers should always be indicated. Circle them, put a box around them, highlighting them's fine. Just need to be indicated. Down here, look at this. We have g of x. There are a number of different letters we use for functions. F and G are the most common. H is often used. But you want to use one of those letters commonly. In probability, we do a probability function with P of x. So there are different letters that can be used. Normally in this class, you'll see F, G, or H, with a couple others thrown in sometimes just for fun. So here we have g of 7 equals 7 squared plus 7. G of 7 equals 49 plus 7. So G of 7, when it's all said and done, it equals 56. So there we are, an overview of functions. The main thing to take out of this is the definition of a function, which is that a function is a correspondence for which each member of the domain has one and only one corresponding member in the range. We'll get much more into depth in functions as we go along.